is just briefly go through your MANOVA homework, and then discriminant function analysis or discriminant analysis, finish up the chapter there, and then get through chapter 8. Then I believe we do not have class next week, right?
Correct.
But I believe your take-home is due in 2 weeks on the 25th, gave you extra time, and the in-class exam, which will cover up to discriminant analysis. So as for your homework, everybody, I just created the variable, and you had 3 options: full-time, part-time, others, correct? The option I created. And then you could see the means. Again, always look at the means. Look at the simple stuff, you guys. What's that? Look at the simple stuff. So here we see, for psychological well-being, the highest mean was for those that are full-time. And we see for social support, the highest was full-time, and others for health scale. Again, I hate others category, but sometimes you have no choice. Just last week I'm working on a project where I forget what the variable was. It was one of the demographics. It might have been ethnicity. We had like 2 Native Americans, 2 Filipinos, maybe 3 Somalians, and then, like 89 Caucasians, 47 Asian Americans. And it's not optimal to do others, but sometimes you will find when you have to feed back demographic information, and if you want to do statistical analysis, you may have to do something about those small sample sizes. And that's the real world. That's the real world. How do we do with boxes M? The P was 0.045. Reject or fail to reject?
Reject.
Reject. Are we happy or sad if the P is 0.045 for boxes M?
Sad.
Yeah. Now, 0.045 is pretty darn close to 0.05. But the fact is, it means that the what is not equal. What is it testing again? Remind me what it is testing.
The variance matrix.
The variance, covariance, and what's on the diagonals at? The variances, right? And what's on the off diagonal?
Covariances.
Right. So if this is group 1 and this is group 2, what essentially we're saying is that the variance, covariance matrix, right? And S21, remember, it's always row by column. So to keep the subscripts, does everybody see this is row 2, column 1? And that's the covariance of 1 and 2. There's the variance of the first DV, the variance of the second DV, and these are the 2 groups, and we sure would love them to be equal. What is this analogous to in the one-way ANOVA? This assumption is analogous to
Identity matrix?
the homogeneity variance assumption. Right. Now, what's an identity matrix?
It's the 1, 1, 1.
Right. So that's sometimes the null model for which assumption? That's the null. What's that? You're close, not quite. Repeated measures. S, P, H. Sphericity. Exactly, sphericity. Exactly. And you're going to see this matrix a lot. I am absolutely tickled pink that there's a Alliant dissertation student I'm meeting with tomorrow who's using some pretty sophisticated stuff because she's got heteroskedasticity in her dissertation. And she's actually using another program which I use called STATA that can actually test for significance. And I've never thought there was a test of significance for heteroskedasticity. You just look at the residual plot. There is. It's called the Brosh-Pagan test. And I found out about it this weekend. And she's actually using these things called robust standard errors. You heard me talk about robust statistics in the regression. Unfortunately, SPSS is not equipped to handle it except for the Hubert-White standard errors. But if you do have heteroskedasticity, there are what's called robust standard errors that you can use in other software. And in SPSS is that wonderful macro, if you want to relive chapter 4 from Cohen and Cohen, the chapter on heteroskedasticity, that can accommodate these types of odd residuals. So we'd love this to be equal, 0.045. So what do some people say if it is significant? Well, we know that this assumption is also impacted by multivariate non-normality. So you could try transformations. God bless you.
I did.
You could try. Did it help at all? No, and that's great you tried it. The problem, the thing is that the only problem I have with transformations in a multivariate context is you're kind of changing the scales of one of the variables, right? So just descriptively, it's going to be odd to report it. That being said, everybody, the p-value for Wilks lambda, the p-value was 0.229. Reject or failed to reject? Did you reject or failed to reject?
Failed to reject.
Right, so we did not have significant differences between these three work groups on the linear combination of psychological well-being, social support, and health. Right? Now, what's interesting is if you use Roy's largest root, 0.052. So they do have these four tests of significance can operate very differently. Usually Pillay and Wilk and Hotelling's, my own experience has been they're kind of similar. Roy's largest root, which is a different ratio of eigenvalues, can operate a little bit differently. Sometimes you have more power with it. That being said, though, we'll just use good old Wilk's. 2.7% of variance was accounted for. How do you explain the effect size in a MANOVA context? Someone try to explain that effect size in a this is a multivariate effect size. Let's go and explain what that 2.7 means.
The power to detect the linear combination or explain it?
The effect size, interpreting the effect size.
Oh, I'm talking about power.
Yeah, I'm talking about the effect size.
Okay. So it explains the variance?
Yeah, but give me a full sentence. I mean, in a MANOVA.
Okay.
I'll start you off. 2.7%.
The variance in the outcome variables is explained by the linear combination of the independent variables?
Almost.
Opposite of that?
2.7 of the linear combination of the outcomes.
The DVs can be explained.
Yeah, the linear combination of outcomes is explained by the independent variable. You got it. 2 point per. There you go. There you go. Now, here's the Levine test, and you see it's not significant for all of them. So what's interesting is the multivariate test was significant. Do you see the univariates or not? Did anyone notice or comment on that? What seemed like an incongruity? So does a multivariate give a different picture than univariate? Absolutely. Absolutely. And then each of the individual tests. These are just like running 3 one-way novas. How do I know they're like 3 one-way novas? Each one has its own unique error term. Right? There's not an omnibus error term, as we were used to in 6021. So here you see you have a unique error term. So this is no different than running 3 one-way novas. And we see none of them are significant. None of them are. And of course, if we had significance, then you can look at the post hoc, the Tukey, or whichever. Again, the Tukey is great if the variances are equal. If the variances are unequal, I would encourage you to use what's called the Games-Howe. That has some very nice properties. So that, everybody, is your MANOVA homework. Any questions? Any questions on the MANOVA homework? Okay, perfect. Okay, discriminant function analysis. What was the primary, there's actually a couple of primary goals associated with discriminant analysis. And I don't know, again, if you're using this book to supplement. This book has some very nice user-friendly chapters on each of these.
I like it.
It's very nice. It does a nice job of supplementing it. And it does, I believe this does have a chapter. It might
like
be.
stats for dummies.
No, I wouldn't say it's for dummies. That's such a harsh descriptor.
Well, I'm referring to myself.
I know.
Because
But
the other book is very, technical.
and this is a non-technical multivariate book. Stevens, if I'd given you Johnson and Wickern, you'd be rebelling. That being said, yeah, this book does a great job of just giving a nice user-friendly. So why do we do discriminant function analysis, you guys? Why do we do it? What's one of the objectives that we discussed last week?
Describing major differences among the groups in ANOVA.
In what way, though? Okay, so go ahead and explain that to me.
I'd have to read farther along in the paragraph here.
Okay, so I have 3 variables, Chad, each of which are probably intercorrelated, as you can imagine.
Yeah.
And what we're doing, instead of having the group variable predict the outcome, casting it as a multivariate regression model, we're doing the opposite.
Vice versa.
Vice versa. The group variable becomes the outcome. Right? So it's like a reverse MANOVA, isn't it? And we're seeing if the linear combination of the predictors predict this grouping variable. And why do we do that? So we want to see which of the variables does the best job of leading to group separation or group classification. So there's two major objectives. One, I can get kind of a beta or a test of significance for each of these, right? I can see which one does the best job of predicting the group outcome. And that's the descriptive part. The other part is for classification. Because then you're going to be able to see is how well, given this linear combination of variables, lead to group classification. And let's make this really easy. Let's say there's just two groups, full-time workers, part-time. Lord knows what's going to happen to those telecommuters after the little Yahoo decision a couple weeks ago. Boy, that's been discussed a lot in business section the last week or so. In fact, there was a big editorial on it in the LA Times, the kind of the pros and cons of telecommuting.
Best Buy got rid of their row program as well.
What's that?
Best Buy was known for their results-only work environment where people could come and go as they pleased as long as the job got done. They just axed that program too.
Separately from Yahoo, or do you think influenced by Yahoo?
It came about pretty quickly after Yahoo, so Yahoo may have
Yeah,
tipped the
Best-
scales, but it was obviously in the works.
Best Buy's got having problems too.
You know, with people with young kids and families, I mean, it's a godsend, you know, having these programs, you know, for
For
families.
night people.
What's that?
For night people who don't function well in the morning.
Absolutely.
Or really early people who want to.
Absolutely, get their work done.
When they're at their peak.
Absolutely. So we do this discriminant function analysis, and as you learned, you're going to get as many functions at the minimum of number of groups minus one or the number of predictors. Right? So in other words, if I have three predictors, or what we call discriminating variables, and two groups, how many functions will I have?
Minus one.
Right. It's either the number of predictors, the smallest, or what's called the minimum, right? It's the minimum of number of k predictors or g minus 1. Minimum, this means minimum of those. So if I have two groups, guess how many functions you're going to have? Just one, which will make life very easy for you. So now, let's go ahead and looking at this example of demo 5, and just so you know again what demo 5 is. Demo 5 is, are you currently in a relationship? Yes or no? And I'm going to have 6 of these predictors. How many functions I'm going to have with 6 predictors and 2 groups? 1. So here you get, do you see these coefficients, everybody? Do you see this constant? Kind of looks like a regression, doesn't it? Doesn't it almost look like a regression a little bit? Each individual is going to get what's called a discriminating score. Each individual, based on their score on each of these variables: exercise, diet, health maintenance, social influence. So just like regression, remember with regression, you took the beta and multiplied it by their score. Right? So it's no different, everybody. No different. And that will be based on what's called the classification function coefficients. And Grimm and Yorn will indicate the above coefficients. The above coefficients, go ahead, get this, can be used for descriptive and or classification purposes. A good discriminant function is one that has much between group variance compared to within. Does that kind of sound like ANOVA? You would love a good function to do a best job of separating the groups, right? And have what? Minimal or maximal within group variance? What's that? Minimum. That would be ideal. So the weights that are estimated result in the best separation between groups. The groups must differ on the D values. D means discriminating. If there's no difference, once you do the regressions, if they come up real similar, you haven't done any better than just flipping a coin. So everybody, now let's get into how you can start interpreting. As the book indicates on page 4, 248, interpret the standardized coefficients, examine the discriminant function variable correlations. And so you're going to see two tables that you're going to use for interpretation. Some people used to say that you use the discriminant function variable correlations for interpretation. Some say interpret them all, and I agree with that. And I'm going to keep with that theme when we get to factor analysis. I would say use all the information for interpretation. So similar to multiple regression, these are standardized coefficients, and of course there's going to be collinearity. And as you remember from 6022, when there's collinearity, be very careful about rank ordering standardized coefficients. That being said, which one is the biggest one?
Diet.
Diet. What's the second biggest?
Self-efficacy.
Yes, exactly. So right now, those maybe do the best job. Those maybe do the best job of leading to between group separation. But be careful about rank ordering importance in the event of collinearity. Right? So we see diet and self-efficacy are the highest. So basically, the standardized coefficient partials out the other variables, right? Think of this as good old multiple regression. Remember, these are partial coefficients. We want to see how well they relate to the outcome, holding constant all the other variables. So you take the unstandardized coefficient times standard deviation for the variable. So for instance, for exercise, we could take negative 0.38 times 1.169. Negative 0.138 is the unstandardized coefficient in a full regression. 1.169 is the standard deviation for that variable, and there's a negative 0.445. So think about what standardized coefficient was, everybody, for multiple regression. It was a function of the beta times the ratio of standard deviation of y over x. So these are standardized coefficients, everybody, and they give you an idea of which one wins, which one does the best job. And then you've got the unstandardized coefficients. See, there's that negative 0.38 that I just showed you. You need these to compute the standardized coefficients. Can I compare unstandardized coefficients and see which one wins? Similar to standardized coefficients, can I compare unstandardized coefficients akin to standardized coefficients to see which one wins? Yes or no? Okay, tell me why I can't.
Because they're measured on different scales.
Yeah, they may be in different. Now, what if they're in the same exact scale?
It's still a different
Different.
construct.
Well, no, let's not worry about construct. Let's not worry about that.
If they're in the same scale, you can.
Maybe. Some would say if they're in the same scale, you can, though there would be some problems because standard deviations might be radically different. Right? And they still have different standard deviations with the variables. Some will be more variable, some will be less variable. So there might even be problems with that. But that is why some people convert everything to z-scores, which I would dissuade you from doing so. However, these are crucial for computing the standardized coefficients, right? Now, what you can use is the structure matrix. The structure matrix is the correlations. So this is the second part, everybody. On page 248, it says examine the standardized coefficients, examine the discriminant function variable correlations. And this is it. It's called a structure matrix. So look what it indicates right there. Pooled within groups correlations. It pools the two groups together between discriminant variables and standardized canonical discriminant functions. Variables are ordered by absolute size of correlation within the function. So you have one function that does the best job of separating the groups, and which one wins? Yes, which comes in second place. Is that incongruous or congruent with the standardized coefficients? You got it, exactly, Chad, exactly. So does everybody see? These have the highest correlation. So these are just like correlations, everybody. What you're going to do to get at that 0.585 you multiply each of the correlations below. You see the correlations? You see this thing called pooled within groups matrix. You're pooling the groups together, and diet and exercise has a correlation of 0.538. Does everybody see that diet and exercise is 0.538? And times negative 0.445. Where's that negative 0.445 coming from, everybody? You remember the unstandardized coefficient? Right there, the unstandardized coefficient, right there. So that's the math behind it, everybody, to get at each of these. To get at each of these correlations. 0.585. So, right now, diet and self-efficacy look number 1 and number 2. Do these look kind of far away or similar? Number 3 is social influence. Does that look pretty close or kind of farther? And I know this is subjective.
Close to what?
To the top 2.
No far.
I mean, do you see what I'm trying to say? You're kind of now making a subjective decision to see are some of them close or enough to say, you know what, I think the 2 big hitters are diet and self-efficacy. And let's look again at the standardized coefficients, everybody, and tell me if you agree. 0.9, 0.772. The next one that follows is a negative 0.445 for exercise. Again, does it seem like there's a bit of a separation? And what might shed insight a little bit into this, everybody? Early on, the first table you looked at, again, it would be nice to have the effect sizes. So you can't rank order by p-values. But notice the smallest p-value was diet. Again, don't use p-values as an indication of effect, but 0.298, 0.437. I could use Wilks lambda, which gets at variance explained. We see the 2 lowest Wilks lambda, right, are the lowest. And do you remember what Wilks lambda was the ratio of, everybody?
Oh, E over T.
What's that?
It's error over
Yes,
total.
exactly, good. The within matrix over total. And what do those lines mean again, everybody? In matrix algebra?
Absolute value?
No, it starts with D.
Oh, the determinant.
Determinant.
That's it.
Determinant. You got it, good. See, Chad? Got it, don't you're enabling the inner staffs within you.
Nightmares, man. Nightmares.
Well, yeah, don't underestimate nightmares. So that being said, everybody, that being said, the structure matrix is akin to factor loadings. And we're going to talk a lot about this in factor analysis. And a structure matrix is the relationship of basically the function and the variable, but it's not controlling for other variables. It's just the correlation. So here it's essentially you have factor loadings where A equals R subscript W D. And what the heck is that? You have a matrix of loadings, then you have a pooled within correlation matrix. It's the pooled within correlation matrix, which is right there. Do you see where it says pooled within groups, everybody? You're pooling the groups together. You're pooling the groups together. And you multiply that by the matrix of standardized discriminant functions. So you kind of see it's nice to have a computer. If you're all interested, everybody, I do have a little cheat sheet here that I did a few years ago for a different sample, and I show all the hand calculations for all of these. I'll put these on camera right here. And you're welcome to look at it at the break if you want. It's got all the hand calculations. It took a little while, but it's just fun to look at. I've never had a class do it by hand. But that'd be a good exercise. So, that being said, these are used for substantive interpretation, everybody. A lot of times people use the structure matrix for interpretation. I think your book may even say that too. I'd have to review what Grimm and Yarnall say. I would like you to use both, the standardized coefficients and the structure. Because hopefully if they're similar, then it's like you've got almost 2 lines of evidence showing which variables do the best job in leading to group classification and separation. So, there's no partialing here for the structure matrix, everybody. For the structure matrix, right there, there's no partialing. It's just the relationship. It's just the relationship. So everybody, some say use standardized coefficients for interpretation, some say use structure, I say use both. And again, I'm influenced a lot by the work by Bruce Thompson in an article called Use of Structure Coefficients in Published Regression is Not Enough. In other words, he says, you know what, look at both of them. Look at both the standardized and the structure. And I agree with that. And I agree with that in factor analysis too. When we get to this thing called oblique rotation, which means the factors will be correlated, you do get this thing called a pattern matrix and a structure. And I'm going to say, look at that. Here's another article. Don't forget the structure coefficients. In other words, look at standardized and structure. So here's your structure matrix. Again, tell me what gets in first place? Diet. Second, self-efficacy. You got it. You got it. Which means you're lucky here. Standardized coefficients rank ordering equals the structure. However, a lot of times they don't agree. This is not unusual. For the structure coefficients, organizational stress, organization commitment, organization involvement. What's number one?
Structure.
Next? What's number one here? Yeah. Does everybody see that? And that can happen, you guys. It's not unusual for the standardized and structure coefficients to not always be congruent in their rank ordering. So that's why I say look at both of them. Look at both of them.
But how would you interpret that then?
That it becomes hard. You know, I'll look at other variables. I'll look at the Wilks lambda, see what's significant. And I'll take into account that maybe there are one or two other variables that I don't want to just easily dismiss. Canonical discriminant function coefficients. Here, difficult to interpret order of importance. Same with linear regression. So akin to regression, here you see the discriminant is negative 0.38 exercise plus 0.876 diet. So here's the unstandardized coefficients. The classification ones you saw earlier were used to create the discriminating scores. And here you actually get the actual unstandardized coefficients. And as Zach said, since they're on the same scale, you might be able to rank order them, but I still would be careful. If we rank ordered these, you would see number one would be self-efficacy, number two would be diet. It would flip-flop. So, and that's because you've got different standard deviations for the variables, right? Especially, even if on same metric. Even if on same metric, they may have very different variances. So different opinions, everybody, on which to interpret. Here's from an article from the American Statistician in '92 regarding the correlations. They say they provide no information about the multivariate contribution of variable. As a result, the correlations are misleading if used for interpretation. Why? Are the correlations, do they partial out? What did I say about the structure matrix? Are they partial or unpartialed results from the structure matrix? Unpartialed. Which means it's as if they're just on their own. So that's why in this American Statistician article, they thought the structure coefficients are misleading because it's not taking into account there's other variables. Those who object to standardized coefficients do so on the grounds they are unstable because they change if some variables are deleted or added, which we know that's true. However, this is precisely the way we want them to behave to reflect their mutual influence. So you see, you get really different opinions. Some say interpret the structure coefficients, the correlations, but those are unencumbered by the relationship with other variables. The standardized coefficients are what? Partialed or unpartialed?
Standardized?
The standardized.
They're partial.
Yeah, they're partial, which means are they taking into account the relationship with other variables like here?
Yes.
Yeah. So you know what? If I could just draw this visually, it would be as if the structures are like this. Do you see why I got rid of the double-edged arrows? There's no intercorrelation, as if there's no. Whereas the partials, or the standardized, take into account what, everybody? Right, the relationships of 1 and 2, relationship of 2 and 3, the relationship of 1 and 3. So again, just to be redundant, I use both of them. Take-home message, everybody. Interpret both. So if I give you an output on your exam, then I want you to interpret both of them. And yeah, Jocelyn, as you said, sometimes they may contradict, or not contradict, but one might be number 1 and number 2 for the structure coefficients, the other might be number 2 and number 1, and that can happen.
So when you say interpret them, if we have the varying ranks, would we sort of just comment on that and say, for this diet's number 1 and this one, the other one's number 1, but in both, you know.
Yeah, comment, absolutely. Like here it looks like diet.
Commonalities and differences.
It looks like diet and self-efficacy does the best job of leading it between group separation to those that are in a relationship or not.
Even though they switch, like, so if we had a situation where they flip-flop, like they're still both the highest.
Yeah,
but
you know what? Exactly, Zach. You know what? Precisely. Right? Think of it this way. In multiple regression, you can have a significant zero-order correlation. Right, everybody? But in a multiple regression, is there a chance it won't be significant? Is it possible that organization commitment might have a nice correlation with leadership, right, style, but in a multiple regression, all of a sudden gets not significant because of the what? Linearity with the other predictors. So all the stuff we learned from multiple regression applies to multivariate. All these multivariate models. Then you get into a little bit of Star Trek type of vernacular, things like centroid. Jim, watch out for those centroids. So what is centroids? Basically, centroids is actually, we learned this from Mahon-Boyd distance. We actually learned this early on from Mahon-Boyd distance, which was a function. Mahon-Boyd distance was a function of basically maybe an individual mean from all these means divided by the standard deviation, and you have a centroid, you have a place in space, and you see how far the cases deviate from that. Do you remember Mahon-Boyd distance even from your multivariate Larry DiCarlo's norm? I think it gives you the 5 top Mahon-Boyd distance, which gets at outliers on the set of predictors, right? Because remember, Mahon-Boyd distance is just a function of sample size times leverage times Hat's matrix. So this can be really helpful in getting at cutoff values for classification. Because you're going to be classified. Either you're in a relationship or not a relationship. You're either low risk or high risk. You're either going to leave the job or you're going to stay on the job. So you get this thing called functions at group centroids. You know, group centroids. You really never have to report or interpret that statistic. Do you see the 0.122 and the negative 0.18? Those are going to be used basically as points in space, where those that are closer with discriminating scores of 0.122 will probably be classified as being in a relationship. Those that are closer to negative 0.18 will probably be classified as what? Yes, exactly. Exactly. So what you're going to find, everybody, when you do discriminant function analysis, analyze, classify, discriminant, and then under statistics, as we said last week, you get all these great matrices, and you can save also predicted group membership. You can predict discriminant scores and their probabilities. You can save all of those for analyses or comparison. And so let's say we have 2 groups. You're in a relationship or not. 87, 59. First of all, what do you think about the sample sizes? Radically different or okay? We'd love them to be equal, but that's not always, in real world, that ain't going to happen.
Moderate.
Moderate, yeah, I mean, it's not perfect, but it's not, I mean, I've seen worse. So here, of course, as you know, you can get a mean, right, for each of these, and you get a standard deviation. And these are actually the means on the discriminating scores. How do I know it's the mean on the discriminating scores? Well, look, predicted group, discriminant function scores, probabilities. So there, everybody, you can get discriminant scores for those in a relationship have a mean of 0.12, for those, negative 0.18. Doesn't that look a little familiar to the centroids? Right? This is exactly the centroids. Remember 0.12, everybody? Just to remind you, 0.12, negative 0.18. And look, everybody, if I save the discriminant function scores, it's exactly the mean of each of these. And look if I do a one-way NOVA on the discriminating scores, everybody. What if I do a one-way NOVA? I get discriminating scores for each one, which is based basically on these regression coefficients. Do you see that p-value 0.076? see that partial eta square of 0.022? Does everybody see that 0.022?
Yes.
Well, let's go ahead and...
What are you doing in ANOVA with the difference between the predictors?
Hang on for 1 second. Not the predictors, no. Let me just add this really quick right here. What you're doing is for each individual, they have their own scores on these variables, right? I may have a 4 on diet, a 3 on exercise, a 2 on self-efficacy, and then I can get what's called a discriminant score, a predicted discriminant score on each of those for that individual. And then that discriminant score, I can get one group and get an average of their discriminant scores and the other on their discriminant scores. So this is those who are currently in a relationship, those who are not, which is going to help with classification. And what I wanted to show you, when I save all of these, Jocelyn, look what I get. If I save the discriminant scores from function 1 for analysis 1, 0.122, make it 0.18. So it's the average discriminant scores.
Within group?
What's that? This is for each group. Those in a relationship, those not in a relationship.
What's the significance mean?
The significance is those discriminating scores are going to help for a classification. And do you recall, everybody, seeing last week the eigenvalue table here? And do you recall that the eigenvalue is 0.022 right there, which was a function of Wilks 1 minus Wilks lambda? So 2.2% of the variance was accounted for. Well, look if I do the one-way NOVA on the discriminating scores. Surprise, surprise, 0.022. So do you see where this all comes together? If I did a NOVA on the discriminating scores for each group, voila, I compare the group, I get the same result as the eigenvalue, which means 2.2% of the variability, right, leads to between group separation. And here's a sample of how you get at predicted scores. Let's say, remember these are scales. They're a function of multiple items and we took an average. So maybe here Ross has a 3.67 on exercise, a 3 on diet, a 5 on health, a 4, etc. So you get the idea, right? You got a score on each one. And here I can get a predicted score, and based on that right here, I get what's called a discriminating score. So there's Ross, everybody. He's got a negative 1.2, which is probably going to put him in the not a relationship. And I can tell because there's the group. That means which group he was clustered in. So here, everybody, I can actually get your predicted group, your discriminant score, probability of membership in group 1 and group 2. You see Ross has a 41% of being in a relationship, 58 not being. Because of course these are always going to add up to what? Probability of being in group 1, probability of being in group 2 is going to add up to 1.0, 100%. So there what's kind of cool is I can get at the probabilities. What would be the worst case scenario for a two-group situation? 50-50. Look at the first 4 people, 43-56, 46-53, 56-43, 41-59. It's a little bit better than Chad's, but not a lot.
Does this data set just happen to have kind of 50s, 40s, or are you going to see sometimes like 90-10?
That's what I would love to see, ultimately. And you're going to see. How can I already tell this is not going to be a great solution?
Because the values are so close.
The values are close. And do you remember the MANOVAs? None of them were significant. Do you recall when you ran? Early on, I could see this was not going to be great because none of these variables, none of these had significance. None of these were significant between groups. So I already know, I would love to, almost exactly what you just said, Zach, I would love to see something like this. For Jocelyn, 80% probability group 1. For Chad, 83 group 1. For Zach, 95%. That would be great. And I bet you I got some good predictors if I have that. Do you see where it's really clear what group we're going to classify them? I can see above that we have scores, right, that have P1 and P2 that do not appreciably depart from 0.5. Hence, you're ripe for misclassification if it's a bunch of 0.5s. So you will multiply the unstandardized coefficient by each raw score and get a predicted score. And doesn't that make sense for each individual? Right? For each individual group, it's going to add up to 1.0 when you add up the scores from each group. So is there any misclassification here, everybody? Okay, keeping in mind again, let's look at demo 5, just so you can remember what it was. Keeping in mind, 1 is, yes, you're in a relationship, 2, you're not. So we see, for this person, do you see that they're in a relationship? 1 equals yes. And guess what we group them in? Guess what they ended up in? Not. So we misclassified that person. There's their discriminating score, and that discriminating score is remember, it's negative, which is closer to those that are not in a relationship, even though this person is. And here they got a 56% probability of being put in to group 2. So you see, what it does is it creates all these probabilities. It computes all these probabilities for each person. For each person. Do you see that we did okay on this one, okay on this one, not so good on that one? So one big purpose of discriminant analysis is for classification. And that's a question that comes up a lot, everybody. Which set of variables does the best job of clustering those who are a good leader versus bad leader? So where D is the discriminant score, G equals group, P is probability. A lot of this is based on Bayesian statistics, where it's the probability of the group given the score, which may seem the opposite, because I go, well, it's the score given the group, but it's the opposite. It takes into account the probability of the discriminant score given the group times the probability of the group sums across all of these. This actually gets into some of the Bayesian statistics. So this is called a prior probability. This is the estimate of the likelihood that a case belongs to a particular group. If you have 2 groups, even odds would be just what? Flipping a coin, 50-50. When you have no information available, you're going to do what's sometimes in Bayesian statistics, sometimes they will call this a uniform distribution. In other words, let's say you have no information. Just put in 50-50. In fact, there's this whole area of stats. It'd be great. I'd love to spend more time learning about this whole area of Bayesian statistics. That's becoming very popular in psychology, where you put in information in the model. Where you put in, and you're going to see more and more people doing Bayesian stuff in our field, I guarantee you. Conditional probability of D given G. It's a conditional probability. Hopefully you remember from probability, what is the conditional probability? Probability of emphysema given your,
Smoker.
yes. Is that different, the probability of smoker given you have emphysema? Yeah, it is, isn't it? Right? That's very different. So the conditional probability of the discriminant score given the group. The group, we already know what they are. The score is a random variable. It's an outcome. It takes advantage of additional information. This is called the likelihood. So in Bayesian vernacular, this is the likelihood, this is the prior. So we take the likelihood times the prior, and then you got, as an outcome, what's called the posterior probability. The posterior is the probability of the group given the data. One way to think about this, everybody, thinking about Bayesian, frequentists, which is what we do, which you've been learned, is the probability of Y, or let's do this, the probability of the data given your hypothesis, right? It's the data given your hypothesis. That's what comes. The Bayesian the probability of hypotheses. Remember that Cohen article you all read? It talked a lot about Bayesian. Bayesian is the probability of hypotheses given the data. It's a very different way of looking at data. Very well, very different. So from M+, Bayes combines prior distributions for parameters with the data likely to form posterior distributions. And it can be used for all types of models, everybody. It's going to be really interesting to see what happens with Bayesian modeling as it becomes just more user-friendly. Even SPSS, I noticed, has a Bayes option.
Are you saying it's going to become more popular because people are going to do more, like gather more data before they...
Well, actually,
have
what's
more?
interesting, it can be used. Sample size doesn't matter with it. It's actually more helpful with small sample sizes. So they find when you have these complex models, small sample sizes, it can be maybe more informative than these structured equation models. They've got Bayes models for structured equation modeling, for regression models, and you actually put in information. Information you may already know. You put in that element of, subjective uncertainty, so to speak. So there's a lot to speak for it. There is a free program. There is a free program. But if you're really interested in dipping your toes in, and I played around with it one summer, but I just didn't have time to really learn the intricacies. There's a thing called WinBugs. And it's free, you can download, and it does. Oh, you no longer have to register to obtain the key. Wow. Okay, I haven't used it for a while. It can do all types of Bayesian modeling. And essentially,
How does this relate to those articles that we read?
it relates a lot, especially to Cohen.
Right.
Very much. That was based
I'm
on.
thin about how he said if you have a large enough sample size, everything is significant.
Absolutely. And look at all these types of projects they've used them on. When you really learn about Bayesian, when you learn about Bayesian modeling, see, look at this. In statistics, Bayesian inference, in which Bayes' rules used to update the estimate for hypotheses as additional evidence is learned. That's very different than frequentist, where you got the data.
Blackjack card
What?
counting is based on, isn't it?
What's that?
This is like blackjack card counting.
I think they use a lot of the Bayesian stuff for some of these probability models. Absolutely. Absolutely. And it's like, this table seems to have about a 63% chance of, you can update and put in the parameter estimates. So it's a very different way of thinking about it. I've played a little bit of Bayesian modeling. I haven't come close to what I would love to. But I'm seeing, even in my regular journals, my applied journals in psychology, I'm seeing more and more articles about the using of Bayesian modeling.
Would you be able to give a real example of something how we might use it in our studies or like in a study?
I think sometimes you could use Bayesian modeling, especially with structured equation modeling, or even at the simplest level is when you have some information. You know that maybe the mean tends to be 2.7 for a group. Well, you can sit there and 2.7, 2.6, have this kind of this distribution of all these possible means and get probability estimates of it. And that's where it can be really, really helpful. It's when you have information. In fact, look right here. Bayesian inference is closely related to subjective probability. So which means you are putting in the information. And this is exactly what we just went over. That's the posterior probability. That's the regular one we do. The frequency is called the likelihood times the prior. And what is that prior in multivariate models? That prior is a multivariate normal distribution. You actually put that in. So sometimes it requires some programming to do it, but people have used this a lot in clinical trials. Where you see this? This is where I've seen a lot. Bayesian and clinical trials. In fact, I downloaded this whole thing. I think that's from the NIH.
Screen, but, yeah.
Yeah, from the FDA. It's got a whole document that guides you how to use Bayesian modeling for medical devices. I had a read on this a few years ago because I was on a project where they were going to do some Bayesian modeling. And they even talk about Bayesian statistics in medical device. They do a lot of Bayesian modeling for clinical trials because they're putting in information. So it's really interesting, and I wish I knew even more about it. I've played with it. Missing data. When I did the presentation, and I'm going to be doing a continuing education here at Alliant on missing data, one of the things is called multiple imputation. It uses Bayesian modeling. It uses Bayesian modeling for missing data. So it's really, it's pretty cool, Zach. It's pretty cool. And that's where you get then, for each case, and I only took the first 10 cases. Here's person number one. There's their actual group. There's the predicted group. There's the probability of discriminating score given the group, as opposed to probability of the group given the discriminating score, right? Prior versus posterior probability. And we can see for this first person, did we do a good job? Actual group, predicted group. How do we do with that person? Did we match them? Did we classify them correctly? How do we do for this person? Right, we already knew that, right? Probability, 56% in that group, 43% in the other. And look, you get a Malin-Boyd distance to the centroid. And soon you're going to learn what this cross-validated
So
means.
hang on just a second. There's one of those Mahalan-Boyd that really stands out, the 4.633.
Okay.
What is that? And
Squared.
it
It's
was a
misclassified.
mismatch.
Yeah, it sure is. That person, the actual group, if you recall, thinking of the actual group, that means they were in a relationship. And oops, we said they're not in a relationship. And we see that the probability is 66%. And that means that person is way far away from the group. In other words, if I plotted this in space, one way to think about this, Chad, is if I plotted this in space, and here's my centroid for group one. Let's say they are in a relationship. Here's my centroid for not in a relationship. Okay? And I've got a person here that was actually in this group. They're not in a relationship. And my score, my discriminating score is right there.
Yeah.
Oops, it's negative 1.10. And they should have been way over here, which means the Malin-Boyd distance, which is the squared difference from that ith case from the centroid, is kind of far away. Again, early on, I knew this was not going to go well. How? How did I know early on, my very first table, non-significance for all the predictors. I saw early on, I know, okay, this is not going to go great. Which means, here's your classification statistics. Here's the second major purpose. So one you got for descriptive, just to see which variables do the best job of separation, and then you get a classification table. You get a classification table where, first of all, each one is, do you see the thing called prior? Just because we have no information, we figure each person has a 50-50 chance of being in a relationship. And you can play with the priors if you want. So based on these classification function coefficients, these are used for classification. These are used, and here's the first group. Are you currently in a relationship? Yep. And this is the discriminant scores. Here's your table, everybody. This is the table you will be using for interpretation, for classification. So here we see 48 people were correctly classified that are in a relationship. Does everybody see they are in a relationship and we predicted? Does everybody see that 48? Does everybody see the 33 for the nose and the nose? Which means 55, 48 out of 87 is 55. 55% were correctly classified in a relationship. 55. It's a little bit better than what? Yeah, it's a little bit better. Is it a whole lot? And you're subjectively, is that a whole lot better? No. So here you see everybody. Overall, 55% of the original group cases were correctly classified. That's it. So now you've seen two major purposes of discriminant function analysis. One is just to see which variables do the best job. We said diet and self-efficacy, even though non-significant. And then we found, overall, how did we do for classifying, for predicting which group they're in? And you know, we're not doing that much better than a flip of a coin. Because here, guess what? These are the people we've what?
Misclassified.
Yes, exactly. We've misclassified. We've misclassified. So, overall, what would I say about this model? It's better than chance, but not by a lot. Not by a lot that I feel comfortable in this model of that those variables did a great job of classifying.
Do you use this a lot?
Not often. Once in a while, I usually use logistic regression, which is going to be your final take home. We're going to compare this to logistic, and logistic doesn't have such strict assumptions. Whoa.
Is that an earthquake?
Yeah.
What is that?
Yeah, that was
Is that
an
an
earthquake.
earthquake? Was
Yeah,
it?
yeah. That was interesting.
I can feel it still.
Oh, you felt
I
it?
saw you make a move and I was like, what is going on?
These guys both felt it before I did.
Yeah, you did feel it, didn't you?
Yeah.
Jolted.
I said I get some of the stats and it's just this, oh, you guys were fine. Let's move
You're
on.
so used to shaking when you're talking about stats.
No, the first
I
time it
usually
happened
drink
when I
enough
moved
coffee.
here, I was on the toilet. And
Yeah, that's it.
And then I got up and I was like, is my toilet loose? And I bent over and I was trying to move it. And then I ran out in the living room and I looked at the cats like, did you feel that?
I had a similar one, but without the toilet part. But I was driving, I was living in Corona Del Mar, which is South Park, Orange County, and I was working in Long Beach, and it was in '94. And there was a major earthquake, not far, I'm sorry, it was in the 80s, it was the Pasadena earthquake, where 3 people died at Cal State LA. And I was driving on Coast Highway, and I was at a stoplight, and it was morning traffic, and my car rumbled, and I just took it to the shop, and I figured, dang, they screwed up again. I had a little, Toyota car. And the guy on K-Rock, which is a big radio station in LA, said, did you feel that? And it was a major earthquake in Pasadena.
It wasn't your car.
It wasn't my car, it was the earthquake. I felt it in my car. Okay, it's okay,
It's
Jocelyn.
not like trees fell down or anything.
Yeah, Jocelyn, it's okay, Jocelyn.
No, everything's still going.
Yeah, it is, the road will still turn. So here, everybody, that's classification. So this is how you can sit there and see how well we did. Notice this other option called cross-validated. This is another option I would like to see you all avail yourself of. What is cross-validation? First of all, looking at the initial results, 55% classified as being a relationship, 55.9. So how did we do? 55.5? Thumbs up, thumbs down. Yeah. What were the red flags that all was not going well? The discriminant function was not significant, right? Remember the eigenvalue? The canonical correlation was small. None of the individual predictors were significant in the univariate analysis. Though it is not implausible that you can have non-significant, univariate, significant, multivariate results. And then when you snooped at the d-scores, the probabilities, a lot were close to what? For the individuals, 0.5. So right then you had all these signs that showed you things were not going well. So for this database, you might as well just flip a coin to judge who will be in a relationship versus not based on the linear combination of our discriminating variables. Well, I mean, we did better. We did 55%. But that's also because we also had unequal sample sizes, remember? And we gave you that correction.
With enough people though, 55 is pretty impressive.
You know what, it might be. Yeah, it might be given the sample size, possibly. You can actually do a z-test in the classification. Z equals chi-square, where z is the observed minus expected over the square root sample size and the square root of expected n minus e. So this is just a little formula that you can get in chi-square, and you can actually get a little test of significance. Now that being said, everybody, I would like you also to avail yourself of the leave one out classification under display. When you get into classification, I want you to also double click on leave one out. Why? Do you see this thing called cross-validated? That's called it's a type of resampling technique. I've talked to you briefly already about things like bootstrapping, which is a resampling. Another resampling is called the jackknife. And what is the jackknife? It literally takes one person out at each time. It literally takes one person out at each time.
How does it decide which person to take out?
Let me show you.
Okay.
Let me just show you right here. Let's say n equals 5. Let's just say n equals 5, okay? Scores equal 1, 2, 3, 4, 5. I'm going to call this jackknife 1, which equals 1, 2, 3, 4. Jackknife 2 equals 2, 3, 4, 5. Jackknife 3 equals 1, 3, 4, 5, etc., etc. Do you see what I'm getting at, everybody? Do you see how this works?
Uh-huh. Yeah.
Do you see how this works for jackknife? I have 5
Yeah.
people. There's their scores. The jackknife, the first sample is 1, 2, 3, 4, 2. There's all combinations, n minus 1, where that score's left out once. That's the jackknife. So it's a resampling technique. So it takes many, many samples. So think if this is only with 5. Think if you had 500. Do you see why you need computers for this?
And it does it to reduce bias?
I don't know. It may reduce bias. I'm assuming to some degree it does. First, it's kind of nice because it can be used maybe for small samples, which sometimes bootstrapping is, even though bootstrapping is not a panacea for small samples. But what it does is it's a type of validation because it's constantly sampling. And you get a better idea sometimes of confidence intervals and standard errors. It successfully classifies all cases but one to develop a discriminant function, and then categorizes the cases that was left out. This process is repeated with each case left out in turn. This cross-validation produces a more reliable function. The argument is that one should not use the case you're trying to predict as part of the categorization process. In other words, use all the other information. And how did we do, everybody, with cross-validation? We did worse. Yes, we did worse. 50%, 44 compared to 48 there. 25 compared to 33 there. 50% and 42. And look what you get in SPSS. 47% are cross-validated. So there's that kind of 50-50, right? When 50-50 can sometimes go, when you have those boundary conditions, it can go either way. So we really didn't do any better, right? We didn't do any better with the cross-validation. But I do want you to use that, everybody, in conjunction with what's called the original, and cross-validated, to be able to make sense of classification. So when all's said and done, we really don't have strong evidence that the linear combination of our health-related variables did a great job of optimizing between group separation, which means maybe you omitted important variables. Could there be other things that predict if you're in a relationship or not? Age, education, money, religious or religiosity, willingness to commit, perceived stability. Add another one, everybody.
Attractiveness.
Okay, yeah, we didn't even have that.
We didn't have any drinking variables this semester, let's still add it.
Oh, okay. Add drinking.
You have like employment?
What do you mean exactly by employment?
Do you have a job or not?
You have a job or not? Okay, so there's a lot that we've left out. So what if I added age, everybody? And income. What if I added age and income? Right? This part is specified, so maybe run another model. And we see here, look what's number 1. Age. Does everybody see that? So someone says, well, maybe you should have age in a relationship. Maybe that's kind of important. It's now 58% and 50%. 58 there, 50 there. It's that much better. In your opinion. In your opinion. Remember, it was 55 and 43, and now it's 58 and 50 once I add age and income. In your opinion, is that a substantive improvement in the classification?
I say, yeah, I still don't think it's, the model itself is fantastic, but the improvement seems to be there.
Okay. Okay, in fact, let's look. Let me see something really quick here. Excuse me, thank you. Let me add Let's add age and income. I want to look at one thing really quick here. Now let's look, I also want to look at actually the eigenvalue and the function.
So it was a 5.2 and ends at,
Oh, really? How far is NSA?
it's not too far away, it's like northeast, still in California.
Oh, what's that about the?
They're as big as Anza Borrego,
Oh, okay.
5.2.
Okay, so looking at basically the novas or manovas, and now we've added age and income. Even though p-value does not say anything about magnitude, we do see lower p-values for age and income, though still not significant. And let's see if the eigenvalues improve from 0.022. Let's see if it's improved much.
0.34.
Yeah, 0.034. So, it's improved a little, not a lot. The function is probably still not significant. Let's do the test of significance. No, p.791. So the function is still not significant. The function is still not significant. 0.791. Right? It still unfortunately is not significant. But we do have better classification, so it kind of helps a little bit. What is a good classification? It's obviously better than 50-50 if it's two groups, better than 33% if it's three. You may desire 70%. There's trade-offs. Because especially when we get to logistic regression, you're going to learn what it means to falsely classify. Because then that's a false positive or a false negative. And there may be trade-offs to false positives and false negatives. What's worse? And hiring someone into a VP of HR position when they shouldn't have, or not hiring someone to a VP HR position when they would have succeeded. In your opinion, what's worse, the false positive or the false negative for hiring a VP into HR?
False positive.
Okay, tell me why you say false positive is worse.
It costs you money.
Do more damage.
More than a false negative.
Okay, so you say false positive, more damage. Anyone make an argument for, anyone, all three people? Anyone out there from Little Rock? Yeah, false negative? Can you think?
The great VP might have had some idea that would have made your company a lot of money. Whereas the person who was bad, maybe it would have been obvious that they were bad. You could have axed them before they did that much damage, whereas the good person may have come in and did a lot of good that you never benefited from.
And obviously, I don't know if you have a class similar to personnel selection. If you had a selection class and learned about the Taylor-Russell table, or gone into any of these types of analyses with what's called selection ratios, base rates. You guys learned it all about that? A selection ratio is when unemployment is high and your pool is stacked with competent people. And my selection ratio is 1 out of 1,000. I get a false positive as a drag because you had many people that were qualified. If the base rate is 80%, and that means 80% of people would have succeeded, and your selection ratio is low, you shouldn't make those type of false positive errors. False negative is going to happen huge, right? Think about UCSD and the UCs right now with admission, undergraduate. Do you think they're rejecting a lot of people that would do well at UC? Absolutely. Because right now, you got a lot more applicants than you do positions. One of my TAs at San Diego State just got accepted at Dartmouth. A really nice PhD program. He's going into cognitive neuroscience. Sharp guy. And he said the people that apply there are only people that are going to succeed. He goes, you don't get many people that are just kind of dipping their toes and seeing where they can get accepted. The people that apply are going to be the ones that would succeed, which means you're going to have 300 people that are rejected from Dartmouth that would have succeeded. So you see, supply and demand matters with respect to what's worse, false positive or false negative. Saying someone should not be promoted when they would have been a wonderful manager, right? False positive, promoting someone when they failed dismally. What are the pros and cons of promoting within and not? And say someone was promoted, maybe they're in over their head, versus not promoting when they could have done great. You might lose that person. That's the false negative, right? So say overall hit rate is 70%. But given the above example, which can you live with? More false positives or more false negatives for promoting? Right? Depends upon your own level of tolerance. Now, what if you have heterogeneous variance covariance matrices, right? What if, looking at, for instance, good old boxes M. Right, keeping in mind, right, remember boxes M. For this one, when I added age and income, happy or sad with a P of 0.484?
Happy.
Yeah. But just so you know, there is an option. You can use, in SPSS, you can use separate variance covariance matrices. In SPSS, you can use separate variance covariance. Or there's a quadratic option in STATA. It's not available in SPSS. The text does indicate multivariate normality is more of a concern. And if normality is not tenable, then you will want to use logistic regression. We introduced that in 6022 for a grouping outcome. And your final take-home, you're actually going to run discriminant analysis and logistic and compare the results. And you'll do that on the second take-home. So from SPSS, everybody, from SPSS, 3 predictors for what's called direct discriminant analysis, what's called the linear method. So again, keeping in mind, this is just a different model, everybody, some other data from a very small data set. 32 people, and we see here classification. We have 3, 19, 15. We did 38% of original cases for this other data set. For 3 groups, what would chance be? 33. So we did a little bit better. 38% there, 31% there. Are we that happy with it? Not really, right? It's not that great. From STATA, everybody, from STATA, here you can see it gives me the same results. I use STATA quite a bit. Everything I can't do in SPSS, I do in this other software. I really like STATA. And here, I just did linear discriminant analysis, and I get the same classification. Same classification. Here's what's called the prior, 33%. Same. Now, what if you have heterogeneous variances? And here's leave one out, which is the jackknife in STATA. Gave me the same results as SPSS. Same results. Now, for heterogeneous matrices, you just hit separate groups under covariance matrix. The default is to use it within groups, pull them together, but just double click or click on separate graphs. I'm sorry, not yet, separate groups. That's all. You just hit on separate groups, which means you'll just go ahead and take into account. You have these separate groups, and we have 43% of original group cases correctly classified. We did a little bit better. Remember, it was about 38%? We did a little bit better with separate groups. So if boxes M is significant, consider using separate variance covariance matrices. And all you have to do, everybody, all you have to do is go into Analyze, Classify, Discriminant. Under Classify, just hit the option there called Separate Groups, if boxes M. I'm not saying it completely ameliorates the problem, but it is an option. It is an option that you may want to strongly consider. Okay, let me close this down here.
Why did you want to do that again?
because if boxes M is violated, if the variance covariance matrices are not similar. In STATA, not available in SPSS, you have quadratic discriminant analysis, which is useful for heterogeneous variance covariance matrices. STATA is actually the programming, there's some point click. You got lines and lines of code in SPSS. Here, a lot of times you can do it just in one line of code in STATA. Discriminant QDA, that means quadratic. And there's the predictors, and there's the group variable. And there it is, the quadratic discriminant analysis. And I can see how well I classified. Here I'll go ahead and see how well I classified and see if it's any improvement. We did 49% for quadratic. Not bad, huh? Remember, it was pretty low initially, so we did a better job. We did a better job with the quadratic. So that's something you may want to consider. Unfortunately, SPSS doesn't have a routine embedded for quadratic discriminant analysis, but there might be a macro somewhere out there. But at least now you know what you can do if the variance covariance matrices are not equal. Now, Zach brought this up last week. What if you have greater than 2 groups? What if you have greater than 2 groups? This would be a weird example, and I'm going to get rid of the last category just because it's such a small sample size. But let's say I wanted to go ahead and see which predictors best predict certain levels of income. Under 15,000, 15 to 30, 30 to 50, 50 to 90. And I know it's an ordinal outcome, but for now, let's just keep it as categorical. And for now, I'm just going to exclude the 8 because it's so small. So now what if I want to see which variables best predict your level of income? So let's use the same predictors just for those 4 groups. Right? So everything is the same. The routine is the same. Giving 6 discriminating variables and 4 groups, how many functions will I have? You got it. 3 functions. You got it. Remember, it's k, the smallest of k minus 1 or p. And in this case, it's 3. You're absolutely right. Do you see self-efficacy is significant? 0.025? And that almost makes sense with income, doesn't it? Do you remember what self-efficacy is?
Belief that you're able to do something.
Yeah, do you think that can influence income? Absolutely. Here's the log of the determinants. How are we doing with boxes M? 0.084.
Okay.
Not bad, right? Which means you don't have to use a separate variance covariance matrix, or you don't have to use the quadratic option. Though it'd still be nice to examine multivariate normality. But now we have how many functions? How many did you just tell me a minute ago?
3.
Things get a little bit on the busy side. Right? Well, all of a sudden you have a true multivariate output. So here we have a canonical correlation for each function. Usually the first one, just like factor analysis, is going to do the best job of separation. It's usually the one that you get the biggest bang for the buck, and we can see the eigenvalue of all the variances, right? If you collapse all the variance, the first eigenvalue has 75% of variance amongst all 3. So do you see the biggest is probably associated with the first function? And the next 2 and 3 still might be interesting, but maybe harder to interpret.
So when you interpret the eigenvalues, what do you say?
When actually with the eigenvalues, 0.38 squared equals 0.145, which does not exactly equal 0.169. When we had 2 groups, we were able to square the eigenvalue to get percentage of variance accounted for. This is actually the percentage of variance from the full multivariate model of 3 eigenvalues.
Okay.
So you can actually get at a percent. When you had 1 function, the squared canonical was close to the eigenvalue, right? So now we have 3 functions. Since minimum number of functions is the lesser of the number of discriminating variables or number of groups. Are any of them significant? Are any of our 3 functions significant? No. Now true, you could use interesting wording like marginally significant, somewhat significant, tentatively significant, somewhat significant, kind of significant, maybe significant.
Approaching.
Approaching, right, absolutely, as if you're kind of putting some type of a, reifying it. Now, the interpretation gets more complex. Because you have 3 functions now. You have 3 of them. So here's the standardized for the first one. Which variable does the best job for the first one? What's that?
Self-efficacy.
Self-efficacy. What does the second?
Exercise.
No. Probably diet and.
Oh, I thought you meant
the
the
second
second
function.
Right. Oh, yeah, no, probably there. They're kind of close, huh?
Yeah.
Here we've got exercise, and then health, self-efficacy, and then the final one, geez Louise, that has small variance counted for. They're all three, I mean, about 4 of these are pretty close, aren't they? Remember, none of them are significant.
So the negative doesn't matter.
Now, the negative is just like factor analysis. You're going to find that it depends upon the relationship of the variable and the discriminant and the prediction, the outcome of the group. Here's the structure matrix. So self-efficacy, then social influence. Right? Self-efficacy, then social influence. Whereas here, it was self-efficacy and then was health maintenance. And look at this, everybody. Social influence is one of the lower ones for the standardized. Look at this. This is when you get those things that are not easy to figure out. Do you see number 2 here? Or diet and health maintenance? Look here when I remove the variance. This is removing the variance. This we see self-efficacy and social influence. Kind of different, huh? And that's going to happen in these types of models. The second one, the big E was exercise. For this one, exercise is. Number 2 would be social influence. Here, number 2 will be health maintenance. So you see, it's very different when you partial out variables versus just looking at the correlation. And here,
Why
the
does
number
structure
one. What's that?
Why does the structure matrix reorganize the variables?
What do you mean
Is that
reorganize?
like
Oh, because sometimes it goes from the largest to the smallest.
because I was thinking they're not in order.
Yeah, no. This one, the first one, it did start with the largest one. If it was just one function, then it would be ordered.
Okay.
Largest absolute correlation between each variable and any discriminant function. Yeah, so just wanted to get at the largest ones for each of these. So you see, you do sometimes get, I wouldn't call it contradictory results. It's just more like supplementary. Zach asked me about this graph last week, so here you go. Here's how to visually capture it. Doesn't even fit. It's called the territorial map.
So what are we looking at there?
I'm going to let you figure that out. I don't use it.
I looked at it last week. I couldn't figure it out.
It shows all 3 functions. Okay, functions for 4 of the groups. For 4 of the groups given their discriminating score. So what you have is we know we have the groups, assuming all functions but the first 2 are 0. So there's function number 2, and it shows me the relationships, where they're plotted in space compared to the centroids for each of the groups. And then this is just the first function. And see here, symbol is, these are the 4 groups, and the asterisk is the group centroid. So let's find an asterisk anywhere here. Yeah, right here. There's an asterisk right there. So you have people. This shows actually all the people and their income and where they place closer to the centroid when you have multiple functions. It's not easy to figure out, is it? No, I've never used it for interpretation. You could probably spend some time with it, and you are more than welcome to, Zach. So you are more than welcome to go to Analyze, Classify, Discriminate, Classify, and hit this thing called Territorial Map. It's not easy to figure out, is it? It's not easy to figure out. And you can get case-wise statistics, again, for every single person. And now there's 3 functions, 4 groups. So, as you can imagine, you get a discriminating score for each of the functions. So you guys, usually there's one major function that does the best job of separating the groups. And the 2 following, may do okay. They may or may not be interpretable. They may or may not.
I'm trying to think about why you would, wouldn't you just ask people, are you in a relationship or not? And they said, yes.
Yeah, but remember, just like regression. Okay, then in regression, why do you ever have regression? Why don't you just say, are you healthy or not, and not worry about predictors? You can I can make that same argument for every single.
Well, healthy's a little bit more.
What if I wanted to predict if you're in a relationship or not?
Just ask.
But what if I wanted to predict and see which variables best predict?
Okay.
Remember,
See what you're saying.
these are discriminated variables that do the best job. Because in the future, let's say you're really interested in I could turn this around for people that are going to leave or stay in organization. Why don't I just ask them? Are you going to leave or are you going to stay? I don't know. I'm going to leave. I'm going to stay. Wouldn't it be nice to have some predictors of that to maybe?
Of course.
So same thing. Same exact.
This would be the kind of thing they did when that Target thing last year got released, where they're talking about how they would predict whether women were pregnant or not before they even knew they were pregnant. You know, I'm sure you heard about it, where they would start sending women coupons for baby products.
Oh, yeah.
When they knew they were
Based
pregnant.
on their buying profile.
Based on their
No,
buying
I didn't
profile.
know about.
And
Really?
so women would start buying like unscented lotions or these certain things that were predictive that they were pregnant, and sometimes before even like the husband or a dad or someone would know. And like the anecdotal story was how the dad got really pissed off at Target for sending his like 17-year-old daughter coupons for diapers and stuff. And then
Really?
he called back a couple weeks later apologizing because
Well,
she
yeah.
actually was pregnant, and Target
Like they
predicted it
did
before she.
Yeah, absolutely. Now what's interesting about that, Target would not have known if they were pregnant or not. Target would not know.
Right.
However, very similar to this is what's called cluster analysis or mixture modeling, when the group is unknown. For this chapter, the group has been known. You leave or stay in a company. You're in a relationship or not. What if you don't know? What if you don't know if they're pregnant or not? But you may have some pretty good predictors based on consumer research that shows which of these variables will most likely lead to group classification. And that gets into what's called segmentation studies in marketing research. A lot of times marketing research, they want to see what segments are there. That's why they ask you for your zip code when you check out. Because they know people in the 92037 in La Jolla maybe buy different things than those who are maybe in different area codes. So they maybe get a little profile on you, and they are able to use what's called cluster analysis, or maybe they probably even do some data mining. I wouldn't be surprised if Target has its own analytics department and does some really fancy data mining for classification when the group is unknown. Remember I told you if I had my dream, we'd add a fourth stats class? And we'd spend 4 weeks on mixture modeling and cluster analysis. These types of pretty advanced, pretty cool tools used for classification when the class or group is unknown. Discriminant analysis, we know it. And I bet you they use something like that.
Cluster analysis.
A cluster or mixture
You
modeling.
gotta try and make a dream come true.
What's that?
There's gotta be a way to make a dream come true.
Anyway,
Anyway.
I've got a buddy that uses, it sounds like, as we understand this, he works for the government in predicting and identifying terrorists. And it sounds like this is the same kind of algorithm that they develop, right?
very, very similar. Very
Behavior patterns.
Yeah, absolutely. A lot of this stuff. Yeah, a lot of stuff gets into the data mining. Some of these they use some even more advanced principles, but absolutely. And there you can get an idea. You can get the relationship of function 1 and function 2. There's that group centroid, right? For those who are under 15,000, 15 to 30. You get an idea if you want to go and look at the relationships of function 1 and function 2 for each of the groups of employment. So there's all these little plots you can get. Individual plots for each of these. And here's the classification. Let's see how we did, everybody. For these levels of income, overall we did 39% for 4 groups. What would be the prior probability for 4 groups? 25%. So in your opinion, is 39.9 better than 25?
Yeah.
Still not great, is it?
With 4 groups.
What is that? Yeah, it's 4 groups, and it's of course a pretty small, relatively small sample size. Well, not that bad. So we could see that we did classification. We did 50% for those 15 to 30, but we did a pretty bad job for 30 to 50, 29%. I'm not very happy with that. And cross classification was 29%, even worse. So again, not great. We did better than chance. 39% for original, 29% for cross-validation. But, so though better chance, are you thrilled with the process that leads to about 60 to 70% misclassification? That'd be like Target sending out 70% of these flyers to men. Right? I mean, just really misclassifying. Again, how do you think you can improve the quality? Find better variables. Self-efficacy was the only significant predictor, so we need to do a better job on model specification. Given the outcome was income, can you think of other variables besides exercise, diet, self-confidence that may culminate in better between group separation? You know, maybe locus control, someone brought up regulatory focus, family background.
What's regulatory focus?
How self-regulation, how much we can self-regulation. So there may be other variables you want to consider. Stepwise, everybody, same caveats as regression. The book does bring up stepwise a little, I believe, towards the end of the chapter. Be very, very mindful about ever using stepwise, because as you know, unfortunately, it does take advantage of chance. But there is the stepwise option in SPSS, everybody. They do have the stepwise option. And just to show you where it is, if you were so inclined, you can go to Analyze, Classify, Discriminant, Statistics. So you can get all the statistics there. And let's go ahead and let me do this really quick here. Let me just define the range, 1, 2. And there's use stepwise method right there. And then you can figure out similar regression if you want to use F values and if you want to change them, just like regression. Just like regression. There's different methods, and that was the shortest output I've ever had. Got rid of everything. Remember, none of them were significant. Do you recall? Wow. Look at this, everybody. Variables entered removed. What are you going to write up, Chad? Are you going to cut and paste that into your report?
Probably.
Probably.
You haven't seen my
So, variables not in the analysis. Yeah, all of them, right. All of them are not in the analysis. How's Wilkes Lambda doing?
On vacation.
And I've showed you this article before, and this is why early on, a fairly well-known journal in our field called Educational Psychological Measurement, as early as 1995, he said they would not take any articles that use stepwise. Medicine still does. I've noticed the medical literature will. I think sometimes because they work with such a large host of variables. If any of you have ever seen a lab test where you got creatinine, albumin, I mean, you got 40, 50 variables. Sometimes they want to see which ones predict. They put tons of variables in. Maybe they want to do a first pass and prune out those. But here, we already know there's lots of problems with stepwise. So again, I discourage you from using it. So with discriminant analysis, this can be very helpful to use after MANOVA as kind of an exploratory technique and or to aid group classification. I mean, that's where I have found it to be very helpful. And see which variables do the best job. For instance, job stat, job involvement do the best job in separating clerical versus management versus executives. See which ones. So you kind of will get that already from your MANOVA. If you think about it, if you have between group differences on a linear combination of variables, then you drill down to your ANOVA. You probably will get very similar results here. But it's just a little different. I like the classification table, and you just get more information. So that's discriminant function analysis, which is really your first technique where we've gone into classification. I don't know how much you remember from 6022 and logistic regression, but it's a close cousin of logistic when you have a grouping outcome. But the mathematics is different. So that, everybody, concludes this lecture. While we go and take 15 minutes, and we will get through Chapter 8 on factorial ANOVA. It's 10:36. We will resume at 10:51. Have a good break, everybody.